Hello everybody, welcome to our last lecture of the year, which is Intro to Kepler's Laws, as well as Newton's Universal Gravitation. This really is focusing on the motion of planets, how planets move, how we're able to predict where they are, how we know their motion. We have this really cool conjunction coming up in a couple of days, and it's totally predictable. We could have predicted it hundreds of years ago, thanks to these two guys. And so we'll go into it. So most astronomers before Kepler believed, as Kepler did when he began, that objects in the heavens moved in circles. This was an idea proposed by Aristotle a long time ago, that things on Earth moved in lines and things in the heavens moved in circles. And Kepler thought the same thing, and so he tried to predict the motion of objects using circles. He said, all right, how can I tell where Saturn is or where Venus is going to be? Using circles. The problem is, when he tried to make these predictions using circles, nothing worked. The math never worked. He wasn't able to figure out where something was going to be at the right time. And Kepler spent a bunch of time on this, and eventually he figured out one of the most important discoveries of his era, which is that planets don't move in circles, but they move in ellipses or ovals. And these ellipses, in many cases, are really close to circles, like our own orbit is, but they are elliptical, and that's something that's important to understand and a little bit different. With this change, he was able to accurately predict where planets were going to be at any given time. And he did a great job of making all of these predictions. He looked all the way back, to the birth of Christ and talked about the Star of Bethlehem like we did in class last Wednesday. And he talked about future and current planet orbits. So his discoveries allowed us to accurately predict where objects were going to be, specifically planets in our sky. And we're going to go over two of his three laws in some detail, and we'll kind of gloss over the third one, and then we'll move on to Newtonian universal gravitation. But in order to do this, we need to start by talking about ellipses in general, and make sure you understand their properties. So the good place to start when talking about an ellipse is to start with a circle. So what are the properties of circles? Well, I think you all know a circle has a center and a circumference, which is the distance around the outside. Of course, the really important thing is the relationship between the radius and the circumference. The radius is the distance from the center to the edge. And then, of course, you could draw a line through the center to the edges, and that's the diameter. Well, ellipses are similar, but they have a little bit different shape. And because of this, we talk about some things in different terms. There isn't just one radius or one diameter. There's what we call the major axis and the minor axis, which are sort of the two diameters of an ellipse. One, the shortest, is the minor axis, and the major axis is the longer of the two sort of diameters of an ellipse. And they cross in the center. But probably the most important, especially in terms of Kepler's ideas, the most important stuff in ellipses are these things, the foci. Foci is plural for focus, and there are two focuses, again, foci, on an ellipse. Where they are, mathematically, is interesting to talk about. You take basically one of the radiuses, the short radius, and take the long radius, and you square them, and you take the long one and subtract the short one from it, and then that distance from the center is the focus. That's a complicated way to talk about it. The fun way to find where the foci are is to take two push pins, put them into a piece of cardboard, and then take a piece of string, tie it around it so you have a little circle of string, put a pencil in it, and drag it around where it's always in those push pins. And if you do that, you'll find where those foci are. And so this is essentially a graphical representation of what I just said. Dragging that black dot or that pencil around with a string attached to those two foci, you're going to end up with an ellipse of this shape. So ellipses are neat structures, and they're really, really important when we talk about astronomy. Well, one thing we can talk about with ellipses is how elliptical they are. A really wide ellipse here with very prominent kind of egg shape to it, very ellipsy, not really a word, ellipses, have what's called high eccentricity. Their eccentricity is closer to the value of 1, which is the highest eccentricity something can have. If you talk about an ellipse that's almost circular, it has low eccentricity, just a little bit wider than a circle. This is still an ellipse, but it doesn't have a high value for eccentricity. We measure eccentricity on a scale of 0 to 1. A 0 for eccentricity, or an E, is a circle. 1 is a line. And so ellipses are all somewhere in between, greater than 0, but less than 1. So here you can see this eccentricity of 0, that's a circle, gets a little more elliptical at 0.3, 0.5 even more so. 0.96 is a very, very big ellipse that looks almost linear. So that's how ellipses work. Well, what did Kepler figure out? Well, Kepler figured out, really importantly, that planets orbit the sun in ellipses, with the sun at one focus and the other focus with nothing there, or an empty focus. And I have it represented here by this little dotted line, but there's not really anything there at all. When planets orbit the sun, they orbit in elliptical orbits, with the sun at one of the foci. But this is how they orbit around, and I apologize for the limitations of the animation. They don't actually stop there, but they do orbit around the sun in this kind of a shape. Now, I know what you're thinking. I spent all this time talking about seasons and how the Earth is not an elliptical orbit. Well, the Earth's orbit is elliptical, but it is barely elliptical. It's almost a perfect circle. But we do get a little bit farther away from the sun during part of the year and a little bit closer during the other part of the year. Turns out we are farther away from the sun during our summer, and we are closer to the sun during our winter. This has almost no effect at all on global temperature. So it doesn't matter from a temperature standpoint, but it does matter from being able to predict our motion. Again, we don't orbit in a perfect circle. We and all planets orbit in ellipses. And here are the eccentricities of all of the planets. The least elliptical is Venus. Venus is almost a perfect circle. And as you work your way up, the most elliptical is Neptune, followed by Mercury and a few others that are very elliptical as well. But planets tend to be nearly circular in terms of their motion. Some more so than others, but they are ellipses. They are not circles, they're just close to circles. When we want to talk about things that are truly elliptical in our solar system, or really have high eccentricities, that's when we talk about comets. Comets have very elliptical orbits. They go really, really far away from the sun, and then they come zipping in, come up close to the sun, and then zoom farther away again. Very, very elliptical orbits, and we'll get to in just a second. They move really slow when they're far away and move good and quick as they come up close to the sun. Kepler's second law describes this motion a little bit and the speed at which objects orbit. I apologize for the imperfections of this animation, but in general what we're seeing here is somewhat accurate. Planets and other objects get faster as they get closer to the sun and slower as they move farther away. How much faster and how much slower? Kepler actually figured that out too. And he did it by what we call the law of equal areas. Planets carve out the same areas in the same period of time. What does that mean? Well, take this planet from this position here, and let's say 2 months later, it's here. So it takes 2 months to make that tiny little path from here to here. Well, if we draw a line between those 2 points and then draw lines into the sun, we get this area, or area 1A. That area, again, is what it's carved out in a 2-month period. Take any other 2 months of an orbit and you'll have another area. So say we take the planet from here to here. Well, here it carves out an area 2. What Kepler figured out is that area 1 and area 2 are going to be the same. That if you have 2 areas carved out in the same amount of time, they're going to be the same area. So whether it's a very, very far out there and it moves really slow, so you have a very tiny slice of pie, or it's really close to the sun, so it's moving fast, and you have a big wide slice of pie, those 2 areas are going to be the same. And that's Kepler's second law. All right. Kepler's third law, honestly, we're not going to spend much time on. He did a good job explaining a little bit more about the orbital period and the relationship between this and distance. It has to do with squares and cubes and all this kind of fun stuff. And he does a good job. It helped him predict the motion of objects. But Newton really upgraded this by explaining it. So rather than getting into detail on Kepler's third law, we're going to move on to universal gravitation and what Newton figured out. So Kepler really marks the end of an era when we explain why things happen in astronomy to explaining what is actually happening. Newton explained why things happen. He explained why objects orbit in ellipses using his laws of motion and his understanding of gravity. Standing upon Kepler's shoulders, as he said, he was able to make a good explanation here. So, what did Newton do? Well, first of all, remember, Newton had already explained the laws of motion for objects here on Earth. He explained to us in his first law that objects continue their motion in straight lines or not moving at all unless acted on by forces. He acknowledged that force equals mass times acceleration. So in other words, force is proportional to the mass and the acceleration of objects. And of course that every action has an equal and opposite reaction. He decided to take these same concepts and apply them to space. He knew, as Kepler did, that objects orbit in ellipses, which is not a straight line. They're constantly accelerating. So if they're accelerating, there must be a force involved. And he thought correctly that this force was gravity. Then it just came down to explaining how gravity works. What Newton determined next was how strong the force of gravity is between any two objects. And this is where he came up with what we call universal gravitation. He knew the same thing that Kepler did. He knew that orbiting objects slowed as they moved farther away, and that they got faster as they moved closer, and that this relationship was not linear, it was geometric. In other words, they got much, much slower as they get farther away. So he put this together, and he came up with the three things that we really care about when we talk about the force of gravity. The mass of the first object, m1, the mass of the second object, m2, and the radius or distance between them, r. These are the three things that matter. If we move the distance up, the force of gravity goes down. Objects need to be relatively close to each other to have much of a gravitational effect. This is why the moon's effect on the Earth in terms of gravity, pulling on the tides and whatnot, is more than the sun in most cases. The sun's much bigger, but the moon's much closer. The other thing that matters, of course, intuitively, is the size of, or the mass of the objects. If you have more massive objects, you have a larger force of gravity between them. So when you take these relationships together, we can start to come up with an equation to represent this. If masses go up, the force goes up. If the radius goes up, the force goes down. So that means that the force of gravity is proportional to the masses and inversely proportional to the radius. So we can write it up this way. The force of gravity is proportional to the masses. Again, that's why the masses are on the top of our equation here. And they're inversely proportional to the radius. So this explains the proportion between them. But if we want to get an equal sign, all we need is a constant. So we know that the units are all working. So we can rewrite this equation as force of gravity is equal to the two masses divided by the radius squared, but times a constant that makes sure the units are correct. On the left, we want newtons. On the right, we're going to use kilograms and meters. If we use this letter g, we can calculate that. And this gravitational constant g, again an uppercase g, not a lowercase one, is equal to 6.67 times 10 to the negative 11. Again, it's not a big number, and that's important because the force of gravity really isn't that large. You have to have very, very massive objects to get much of anything out of gravity. So this kind of controls for that. You got to have a lot of mass, you only get a few newtons out of it. So how does this work in practice? So let's say I want to figure out what the force of gravity is between these two objects. One object with a mass of 800 kilograms, the other with a mass of 1,000, and a distance of 60 meters between them. So first of all, when solving an equation like the one we have here, I always like to write out my variables. So what's my force? Well, that's my unknown. That's what I'm looking for. Mass of object 1, 800 kilograms. Object 2 is 1,000. The radius is 60 meters. And of course I need g, which is a constant, 6.67 times 10 to the negative 11. When I set up my equation, I just replace the variables with the values. And so here's what I have to start with. 6.67 times 10 to the negative 11 is g. Mass 1, mass 2, 800 and 1,000, all divided by 60 meters squared. Don't forget to square that. A lot of times when students are doing this assignment, they forget that little 2 on the bottom, and it's of course really important. So as I work my way through the math here, all I did at this point was I squared and multiplied a bit. So 800 times 1,000 becomes 8.0 times 10 to the 5th. And 60 meters squared becomes 3.60 times 10 to the 3rd. Notice I converted them into scientific notation. Again, I just think it's better to write those things out that way. I could have written 800,000 and 3,600 if I wanted. Okay, from here, I'm going to multiply my values. So 6.67 times 8.0, and then I'm going to subtract exponents. And so I get this. I get 53.36 times 10 to the negative 6th. I could clean that up by moving the decimal over and making it 10 to the negative fifth. In this case, I'm just going to leave it and divide. So here, 53.36 divided by 3.6 gives me 14.82. And then since I'm dividing numbers, I subtract the exponents. So negative 6 minus 3 is negative 9. So my value becomes 14.822 times 10 to the negative 9. Now, since this is my final response, I do need to correct it as scientific notation, move the decimal over, convert it to scientific notation, and I get this really small force. Two small objects, relatively small objects, at a distance of 60 meters have very little effect in terms of gravity. This is like taking a piano and a rhinoceros and putting them 60 meters apart. There's really not much going on in terms of gravity between them. They don't go hurtling towards one another. So when do we actually see the force of gravity play a role? Well, it's when we talk about much, much bigger objects, like the Earth. So I mentioned before that weight is a force. It's how hard you push down on the Earth with. Well, what is that force? Well, we can use universal gravitation to calculate this. Now, in this case, our two objects are you and the Earth itself. So when we talk about the distance between the objects, we're really talking about the distance between where you're standing and the center of the Earth. So we use the radius of the Earth for this value. And the radius of the Earth is 6.38 times 10 to the 6th meters. For our masses, well, one of the masses is the mass of the Earth, which is gigantic, 5.98 times 10 to the 24th, and the second mass is me. And so for me, I have a mass of about 105 kilograms. So these are the values I'm going to use to calculate how much I weigh on Earth. So again, listing my variables, force is what I don't know. My mass is 105, the mass of the Earth, 5.98 times 10 to the 24th, and the radius between us, again, between the center of the Earth and me, is 6.38 times 10 to the 6th. Incidentally, when we're talking about big planets, they're so far away that the radius of the planet doesn't really matter, and we really just talk about the distance between them as the radius. But if you had things that are close enough, you really do want to measure from center of one object to center of the other. Okay, and of course g here is 6.67 times 10 to the negative 11. When I set up my equation, here's what I see. I set up those three values on the top, g and the two masses. On the bottom, not forgetting to square it, I have the radius of the Earth. Punch on through here and do some of the math. Here I've already put them into scientific notation. When I multiply 105 times 5.98, I get 6.28 times 10 to the 26th. I did have to move the exponent there and the decimal to get that. And then, of course, when I multiply 6.38 times itself, I square it, so I'm multiplying it times itself, and I double that exponent. So 10 to the 6th becomes 10 to the 12th. 6 times 2 is 12. If you wanted to write it out, just go through the same process we had before where you add exponents, you could do that too. 6.38 times 10 to the 6th times 6.38 times 10 to the 6th, then you'd add those exponents. But when we have an exponent inside a bracket, we just multiply it. So a little bit of moving around, 4.07 times 10 to the 13th. Continue the process, multiplying things together, 4.19 times 10 to the 16th over 4.07 times 10 to the 13th. Do the math here. I get 1.10 times 10 to the 3rd. And then that to me is a number that's small enough that I'm going to go ahead and write it in normal notation, and it's 1,100 newtons. So, how much do I weigh? Here on Earth, I weigh 1,100 newtons. That value will be different for you because you have a different mass. Mine's 105. Yours is going to be whatever you are in pounds divided by 2.2. And that's what value you're going to use for your mass. If I was on a different planet, that planet would have a different mass and it would have a different radius. So my weight would change. My mass would stay the same, but with a different R value and a different M value for the mass of the planet, I would see a different value. All right, so hopefully you have the information you need to fill out the rest of your universal gravitation worksheet. If you don't, come to office hours. Best of luck to you.